we know that if we take all of the points in the xy plane where x squared plus y squared is equal to 1, we get ourselves the unit circle. Let me draw the unit circle. That's my y-axis. This is my x-axis. And the unit circle has a circle with a radius 1. So that's x is equal to 1. That's x is equal to -1. That's y is equal to 1. That's y is equal to -1. And the unit circle looks something, let me draw it, something like this. I think you get the point. Let me see if I can fill it in a little bit better. So you realize that it's not a dotted circle. So there. That's my best attempt at drawing the unit circle. And we also know that the traditional trig functions, or maybe we should call them the circular trig functions, are actually defined so that if you parameterize, so if you were to take x is equal to cosine of t and y is equal to sine of t, then you pick any t right over here, and by definition, it's going to sit on the unit circle. By definition, x squared plus y squared is going to be equal to 1. So you pick any t, it's going to sit someplace on this unit circle. Or another way to think about it is, as if you start to vary t, you're going to start tracing out this circle. And we know that t corresponds to the angle with the positive x-axis. So in this case, that right over there is t. Now, wouldn't it be neat if there were a similar analogy for not the unit circle, but something that we could call the unit hyperbola? So that's our little review of trigonometry right there, traditional trigonometry. Now let's think about the unit hyperbola. Well, x squared plus y squared is equals 1 is a unit circle. Well, I'll just say that x squared minus y squared equals 1. I'm just going to call it my unit hyperbola, or unit rectangular hyperbola. Hyperbola. And this is just a little bit of a review from conic sections, but it would look something like this. It would look something like, now I actually want to make it completely analogous. So it would look something, so that's my y-axis. This is my x-axis. And then we can say, well, if y is 0, x could be positive or -1. So I guess you could think of it that as kind of the unit part. Where does it intersect the x-axis? So that's +1. That's -1. And then it has asymptotes y equals x and y is equal to -x. And we go through the intuition on that on the conic section videos. That's y equals x. Y equals x is that dotted line. Y equals -x. Is that dotted line right over there. Y is equal to $-x. And then this thing is going to look like this. It's going to have a right half that does something like this. This is all a review of conic sections. It gets closer and closer to its asymptotes. So just like, or 2y equals x and y equals -x. And the same thing on the left-hand side. It's going to do something like that. Wouldn't it be neat if we could parameterize x and y's in a similar ways with different functions, maybe like analogous functions, so that we get a similar type of property? And you might guess what those functions are, but let's actually try to verify it. What happens? What would happen if x is equal to our hyperbolic cosine of t, which is the same thing as e to the t. Let me write a little bit different. E to the t plus e to the -t, all of that over 2. And y were to be equal to hyperbolic sine of t, which is equal to e to the t minus e to the -t over 2. Wouldn't it be neat if there were an analogy here? If you over here you picked any t in our and based on this parameterization based on our circular trig functions, you ended up with a point on the unit circle. Wouldn't it be amazing if for any point t over here you ended up with a point on our what we're calling our unit hyperbola? Well, in order for that to be true, with this parameterization, x squared minus y squared would need to be equal to 1. Let's see if that is the case. So x squared minus y squared is equal to, well, let's square this business. It's equal to e to the 2t plus 2 times the product of these two things, 2 times e to the t times e to the negative t. Well, this is just e to the 0 right over here, which is 1, plus e to the negative 2t, e to the negative t squared, all of that over 4. And then from that, we will subtract y squared, minus, so the numerator is going to be e to the 2t, minus 2 times e to the t, e to the negative t, and then plus e to the negative 2t, all of that over 4. So immediate couple of simplifications here. E to the t times e to the negative t, that's just e to the t minus t, which is equal to e to the 0, which is equal to 1. So this is going to be 1, that's going to be 1. And so we're going to have a 2 in either of those cases. And if we were to simplify it, all of this stuff right over here, I'll do it numerator. So this is going to be equal to, over our numerator of 4, e to the 2t, plus 2, plus e to the negative 2t. And then we have minus e to the 2t, I'm just distributing the negative sign, plus 2, and then minus e to the negative 2t, Well, this is convenient. This cancels, oh, that's hard to, I was writing it in black. Black's not an easy color to see. This, let me do it in green. This cancels with this, and this also add up to 0, and you're left with 2 plus 2 over 4, which is indeed equal to 1. So this is a pretty good reason to call these two functions a hyperbolic trig functions. These are the circular trig functions. You give me a t in these parameterizations, we end up on the unit circle. You vary t, you trace out the unit circles. Here, for any real t, we're going to assume we're dealing with real numbers here. For any real t right over here, we're going to end up on the unit hyperbola right over here. And in particular, we're going to end up on the right. So it's not exactly over here. Pretty much any of these points could be parameterized right here. Over here, we're going to end up on a point on the right side of the unit hyperbola. And the reason why it's the right side is you go straight to the definition of cosh t. This thing can only be positive. This thing can only be positive. E to the t can only be positive. E to the negative t can only be positive. So this is only positive. But you give any t, you will end up on this hyperbola, specifically the right side. If you want points on the left-hand side, then you would just have to take the negative cosh t and the sine, the negative cosh t and the sinh t to end up right over there. But it's a pretty neat analogy. We were looking at Euler's identity, and we kind of said, oh, well, let's just start playing with these things. And, you know, there seems to be a similarity here if we were to remove the i's. And all of a sudden, we've discovered another thing, that there is this relationship here, where there's a relationship between these trig functions and the unit circle. Here, between our newly defined hyperbolic trig functions and the unit hyperbola. And you'd also find if you were to vary t, it's going to trace out. Just as if you vary t here, it traces out the unit circle. You vary t here, it will trace out the right-hand side of the unit hyperbola for this parameterization right here.